Very proud to be here. So let me go through what we're working with. We're talking about placental mesenchymal or mesenchymal. What have we decided now? Mesenchymal stem cells. And these are our exosomes here by electron microscopy. But what I want to talk about going forward is how to characterize exosomes in other ways. So we know we can get exosomes from many places, but in 2014, when I was working with conditioned medium, I didn't know what an exosome was, and not a lot of people did. Now, there's some of you did, because the first International Society of Extracellular Vesicles conference was in 2012. But seeing what was going on with conditioned medium, being that I have a PhD in biochemistry and immunology, I did not understand how proteins were persisting in a conditioned media culture long enough to get the outcome that you're going to see here. And so that sort of led me down this road of trying to figure out what's going on. How are we protecting these proteins? And now getting to an understanding that, hey, maybe it wasn't the proteins. Maybe it was the microRNA and messenger RNA protected in the lipid vesicles. So that's what I'm interested in now, but what has really been sort of a driving force for me is to see these kind of outcomes. This is the daughter of one of my employees, actually. And so not having this product in the freezer that you can use at the drop of a hat is really a scary proposition for me. I've been to Barcelona twice, cut myself, and the wound won't heal. I come home, I apply the exosomes, and 3 or 4 days later, the wound is resolved. So this is what really drives me. I got into this because through bone marrow transplantation. My father had acute myeloid leukemia, and so I've really been into cell therapy for quite a long time. Everybody here knows this image, I'm sure. But this is the manufacturing process we're talking about now. I like to call the placenta the olive tree. I grow the olives and I isolate the olive oil, and then I characterize the olive oil. And I like this system as opposed to some tissue engineering because, well, what happens in the regenerative medicine clinical world is that I can fully characterize this. If I take a placenta, grind it up, and filter it, I can't really characterize that. And certainly I thought the FDA was never going to approve that, although they've allowed some INDs to go forward lately. But this is what I saw on a dish in 2014. I had some MSCs over here that were not growing and some MSCs that were. So by taking the conditioned media from that and putting it on the older cells started to grow. Now, you can't really be selling conditioned media for any kind of intravenous administration, so I had to start figuring out how to isolate that. But I was sure that what I had seen was true because you can look at these reports, and we have a 40-year-old in this older paper up here, in vitro secreting profile of human mesenchymal stem cells, and then down here, you look at the secretory profile of that, and there's quite a difference and quite a lot more proteins and messenger RNA in that younger exosome. So I could see what my cells were doing, and then I started wondering what the exosomes could do. A lot of people are working on this now. This is from Jeff Bezos's system, what is it called, Axios, that he invested in. But this is really good data. This is Horvath's group. And you can see that young adipose-derived EVs can cause this kind of regeneration rapidly. And then you look at increase in type 2A fibers, decrease in intramuscular fat deposition, and my favorite topic, epigenetics, right? So anybody who's going to start treating somebody in regenerative medicine from now on should absolutely give them an epigenetic test first. If not, other tests. I mean, telomeres, but if somebody in here wants to tell me how you're going to get bone marrow out to do a really good telomere test, I know how, but I mean, who's going to actually do that? But they could see a decrease in the epigenetic age of these animals over time, and that's exciting, and that's what we've been seeing in the clinic. But this is where I have arrived as to how I can characterize an exosome for reproducible GMP-grade clinical exosomes. So we have to use every one of these systems, and what we're going to get to is a unit that I would maybe encourage. I mean, we thought about this unit for a long time, and trying to say particle number is very inaccurate, and I think that this formula might be a good one. But first thing to know is whether you have a population of exosomes, and certainly we can demonstrate that at about 100 to 120 nanometers. But what about the mRNAs? So we look at our microRNA profile from lot to lot to lot and demonstrated that to the FDA, and I was hoping that that would be good enough. It wasn't, but it was definitely part of it. That's why, but it is definitely, in my mind, better to characterize than just looking at these particles in a dish. It's just ridiculous. And when it came out and I didn't know what I know now, I mean, I literally drove one of our techs crazy because the protein concentration was never correlating with the particle number. And she's running around saying, we don't have anything, we don't have anything, and you know, she went crazy. So, but if you look at particles in this is tap water, and so we're showing the same types of particles that you can see elsewhere. So I've tried a lot of things, atomic force microscopy to look at the vesicle, other types of EM, and those are great, but you know how long it takes to set those up. So when I was demonstrated this D-storm microscope, and specifically this image of a mitochondria, I was kind of sold on this machine, even though it was very expensive, but I thought, you know, this is going to allow me to know what I have. And certainly by light now, we can see what our exosome looks like and look at the surface markers of said vesicle. So at least we know that we have what is a definitive exosome, right? But does it really matter if you have 63, 81, or 9 on the surface of a vesicle if there's nothing in it? Is it going to be therapeutic? And certainly if there's nothing in it, I'm not interested in it so much having that, but I'm not going to call it an exosome unless I can prove that that's there. So it must be identifiable, but it must be effective. So what we've done is we've come up with this formula which states that A is the RNA concentration, B is the protein concentration inside of the vesicle, and C is the total protein concentration. So in this fashion, we can correlate protein to RNA and try to have some kind of reproducibility. Now, we have to show that the exosomes are taken up, so we can see that they're taken up within an hour, all right? So now we know what they are. We can call them an exosome. We know that they're taken up. This got approved 3 weeks ago. But, you know, we wanted to know what the distribution was as opposed to what's in the literature. And you can see here, but from Charles River Laboratory, with IV tail injection of exosomes, we can see that they go to the spleen, which is reported. They also go to the brain. But our collaborator at City of Hope, Karen Abudi, pointed out to me, I thought this was an injury and the exosomes were going there. And she said maybe they just missed. And I thought that's a lot more probable, because I've certainly missed lots of mice in my time. But what is interesting to see is that the exosomes still traffic to the spleen and also the brain, which is a strange thought, that you could give somebody a microneedling treatment on their face and maybe be giving an anti-aging treatment over time. So again, that was 3 weeks ago. It's an IND for COVID, but as you know, what's important is that that CMC was approved, and now we have many other ideas of what should be done. But towards the end of HLA rejection, et cetera, it's a human exosome. You can see in this horse who's applied topically with these exosomes, this wound is resolving in 30 days. And that's what we want to see to try to prove that they're non-immunogenic. Now, they are human exosomes, and I've never wanted to say that there's no HLA on them, but they are very small. It's a macrophage can take it up, but it can't really recognize it. But interestingly, in a model of graft versus host disease, in a mouse, a human exosome will be recognized, and those mice lose weight faster. So it makes it difficult for that type of study when you don't have the proper model. Don't know how we're going to deal with that in the future, but you know, that's a product we call exosome. And then here's the dog of that collaborator, Karen Abudi, who couldn't walk, arthritis in the hips. So she applied the exosome sub-Q, and then this is him walking around the next day. So I've got my animal models, okay? Maybe there's an N of 1, but you know, I'm trying. So this was my first lab in 2014, 15. And one of the reasons I had to scrub that floor myself and paint that floor, there's when I had to work, and I don't look like I'm having a very good time, right? But now we operate a 27,000 square foot lab in Miami, and how does one accomplish that? Well, the exosomes work. And we sell the exosomes all over the world. I have a number of collaborations in Spain that we're working on, as well as South America. But that's the third of 4 clean rooms. And I really pride myself in this GMP staff that we have. So whereas I'm already said, I think this is the best regenerative medicine institute in the country, you know, I don't know how much you can produce here. And certainly as these therapies grow, you're going to need more bandwidth and space. So I hope that in the future, if anybody's interested in exosome work, keep us in mind, and that's why I traveled all the way up here to see you. So I can speak for 8 hours straight, but I thought this was a 20-minute talk, and you've all been sitting there for a long time. So I'm going to end with that, and if you want to see the lab, you can scan that. And thank you very much. ligated proteins on the surface is coming. I mean, I'm working on it. So I think we'll get there pretty soon.
Okay. And you use, for clinical applications, you do exosome purification in larger, exosome purification in larger quantities. So is that a do you have methodologies that will take care of the heterogeneity that exists in an exosome population?
Well, that's a good question. I mean, if you look at that image from the D-storm, that's a very, very heterogeneous population, which is kind of why I know it sounds heretical, but I don't care about exosomes. I care about therapeutic outcomes and then the amount of RNA in that solution, the amount of proteins in that solution, and that's going to correlate to a number of exosomes, yes, but does that really matter? And I think what has happened with everyone, I mean, even the FDA said, why don't you make your release criteria the particle count? And I'm like, no, we're not going to do that, you know? And I had to argue that point. And these clinical exosome products that are out on the market, they say, oh, I have 1 billion, I have 1 trillion. I mean, you know, I actually have 2.4 quadrillion particles if you want to go that route, you know, but that's not going to help. But it's an ongoing question. And right now I'm just going to stick with, that's why I created that unit. And I think that that's an effective way to do it. I haven't heard anything else like that. If somebody else would like to clarify it for me, I would appreciate it. But I think that a unit, just like Botox is sold in a unit, is a more appropriate method.
And if you were to use a zeta view, you will get a different number. If you use a nanocyte, you will get... Okay, so if you use a zeta view, you will get a different number. If you use a nanocyte, you will get a different number. Depending on what you're using to quantitate, you have a wide variety of numbers that you get on the same batch of exosomes.
Well, you can, right, the exo view is a pretty good product, but again, it's showing you the number, it's just showing you the number of exosomes, and they do that by binding the exosome. A nanocyte, for instance, say, well, when they sold it to me, you can have a 488 laser on it. Okay, great, well then I could put some of these markers and I could quantify. Well, then we found out that, oh, it's not powerful enough with these exosomes moving around to actually see it. So they had never actually done that when they sold it to me with that idea, you know. So I've been doing this since before the hardware existed, and as the hardware has come, now we're getting to a better understanding. But knowing that, like with the ExoView, that you have 63, 9, and 81 on the surface and Alex inside, that still doesn't tell you if it's a therapeutic exosome or if it has any interesting content, you know. So, yeah, do we really want to get to that understanding or not? I mean, we just got to single cells a few years ago, right? I don't know if we're going to ever get to single exosomes.
And the last question I have for you is targeting. Do you have a technology which is proven in clinic or at least studied well enough to say that this batch of exosomes, I can target it to this specific compartment in the body?
Well, that's the benefit of knowing that we need 63, 81, and 9 on the surface. You know, I saw an interesting talk once that 9 was only on younger exosomes. But if you have 63 and 81's on the cell surface too, but you can make whatever you want, attach it to that 63. Now you're going to have to look at the immunogenicity of that, et cetera. But it gives you that value. I mean, that's a good...
Is this something you do in your laboratory?
That's something we have going, yeah.
Okay.
For brain targeting.
Thank you.
Here. So you got approval from the FDA.
Got approval after much consternation.
Is this for human, animal?
Human. For human IV administration for post-COVID symptoms. Oh. Now, will we actually do that trial? I'm not sure. I mean, because I put it in when COVID was a very big issue. And actually, they said to me, our risk-reward calculus has changed. I mean, they don't want any more COVID issues over there. And that's why it was so hard. I had to do a type A meeting. I had to do all kinds of things. And make a lot of data. I had to characterize the cell line the same way as if it were a cellular therapy. And our argument was, we're not even using the cells. We're using the exosomes. We characterize the exosomes. No, you're going to have to do both, down to the wire, down everything you could possibly do. Yeah.
Any questions for Duncan from the audience?
Oh, I also went through a 2-week inspection. That was fun.
I'm sorry?
2-week GMP inspection. Yeah, that was awful.
Oh, thank you so much. Appreciate it. Hello again.
This is for Dr. Ross. So just any comments you'd like to share about organoid models or any ways to sort of compare all these biologics that are emerging in a meaningful way?
Yeah, I love fibrin. The idea of, I really am interested in, what you should think of is that nano-encapsulation, or encapsulation in a diabetic model of islet cells, I think that's so cool. Keep the immune system away from it, you know. So you could think of using those, putting those islet cells in that matrix and then encapsulating it away to keep them as third parties away from the immune system. That's a fantastic method. And you could think through that to other organoids such as kidney, et cetera. And then you could get away from a lot of these HLA problems that everyone here is successfully working on, but those are very difficult methods. Yeah.
I have a quick question for Duncan Ross on the exosomes. What's the difference between exosomes derived from BMAC, Wharton's jelly, and yours is placental derived? So that's amniotic fluid? Or?
Placental cell line. No, I have to apologize to everybody because I am part of this group that went to the clinic before they went to research. All right. So what has happened is that everything is being called an exosome. So I used to make an amniotic fluid exosome, and you could see some markers like CD81, but when we ran the RNA concentration, there was no RNA in it. There was very, very little. So when you see somebody says a Wharton's jelly exosome, that means that they're taking an umbilical cord, grinding it up, filtering it, and selling that within 24 hours. I was actually going to give it away for free as a loss leader because it's so cheap and easy to make, and there's no characterization. Now you could have the Ebola virus in that. You have no idea. So I was never really too chuffed about that idea. If it was an umbilical cord MSC, they would state that, meaning that they're expanding it. And you can't really call something an MSC until you expand it because of the cell surface markers and the requirement to differentiate it to cartilage, adipose, and bone. So those are the dog whistle of where it came from. Is it a tissue product or is it a cell therapy product? And mine is a cell product, and I usually have that slide up. Do not call this a tissue product, because if you say that in Europe, you are never, ever going to get approved. And in fact, I had 3 regulatory people refused to even work on the regulatory because I didn't know how to successfully get that idea through their head. So that is a pretty key indicator there. But when we looked at all of those tissue products, not a single one had RNA in it. So there's something about this culture system that is creating this RNA. And
how sensitive is it to passage number?
It's a little sensitive. But we're using max P4, and using, as long as you don't use serum, you can do pretty well. Yeah.
Anybody else? Okay, not right now.
Okay,
Dr.
I can go
Devakumar.
ahead. So the next questions I'm going to ask would be for the reprogramming people. So both of you can answer the question, Mike and Ellen. So what needs to happen from a regulatory perspective to actually take the reprogramming technologies that are emerging to the clinic?
Hold the microphone like this. Dr. Ross gets an A+ for this. Hold it like this. This is how you hold the microphone when you're going to talk. Thank you.
I know nothing about the clinic. I'm sorry.
You don't want to answer the question?
About the clinic?
Yeah.
I don't. We're not near the clinic.
She said they're not near the clinic. What I described, how's this? Is this good? I think it's that you don't want to hear your voice reverberating back at you like a rock star up here. So, what I described is not near the clinic. there are some people working on partial reprogramming technologies utilizing different methods, right? mRNA, there's been discussion about exosomes or extracellular vesicles to deliver gene therapy, which has really been our primary focus, and or other, small molecule drugs as a cocktail to accomplish that. Each would have their own regulatory pathway. Some people in the field, I won't name names here, but some people in the field have said we're 2 years away from an IND. I think that's a bit optimistic. I purposely laid out sort of a transparent and candid view of what we're dealing with here. Reprogramming, like iPS cell reprogramming factors, can take a skin cell 180 degrees across the globe, back down to Singapore, back to the beginning of life. That's a really significant alteration in the phenotype of a cell. Now, okay, we're saying partially reprogram. We're just transiently expressing factors capable of reprogramming cells back to pluripotency or a subset of those factors. But still, what I tried to allude to is these factors or the regenerative state is, I think, not purposefully, has been selected by evolution and by natural selection. I'm not trying to get teleological here. It was selected for as a tumor suppressive mechanism. And so FDA, rightly so, I hope, is going to be all over the technology about safety. Ellen's approach is, I think, far less problematic. Maybe you would disagree, but I think the approach she's taking is, has less ideological baggage carried with it. But partial reprogramming, I've been as enthusiastic as I can be about the potential of the field and where it's going to go. We've got a lot of work to do. But the safety concerns are going to necessarily have to be addressed in depth. And there's a lot of work to be done. But the potential is, I was sitting here as the panel was sitting down, and I was thinking, what I would like to talk about. I won't try to change the topic of Q&A, but I really feel strongly that those of you that are here today, we all have a common interest in advancing this field, and the problem the United States and other countries are facing with what I talked about, the chronic degenerative diseases, is going to bust the bank. Duncan, well-known economist and financial guy, just gave a talk at UC Irvine, I think, with a very candid appraisal of where the United States is headed. And he came up with this number of $200 trillion net present value of our obligations under our entitlement programs to the aging population. What is that? $200 million?
Well, you're looking at me.
You're the intellectual here in the panel. You can do the math.
A lot. It's a lot.
Right? $200 million. What is it? 300 plus million in the United States. That's almost $1 million a person. And his point was, well, we're not going to meet that need. The United States can't do it. It's not even budgeted. Zero is budgeted for this. So I really would like all of us to try to impact as much as we can policymakers in the United States and around the world to take a hard look at the technologies we're talking about in this conference. It's not just a matter of health for the individual and the suffering of individuals, it's also the fate of our countries. It's a very serious issue. I wish we could get the attention of people on it. So sorry to get on my soapbox, but I just wanted to say that.
No, that's absolutely relevant. Thank you for that, Mike. That's absolutely relevant. Thank you for that, Mike. So, Ellen, there are a lot of people working on trying to reprogram cells and tissues using Yamanaka factors. There have been approaches using chemical means to reprogramming cells, and your approach is also, the data that you presented was phenomenal. So why aren't too many labs working on similar approaches such as yours? Why is there such a mad rush to use Yamanaka factors and reprogram cells? And of course, Mike rightly pointed out all the problems that could exist in that pathway.
Well, I guess to be cynical, it was published in Nature. But, well, I mean, we found, again, through this mouse that has really incredible regenerative properties. I mean, besides the things I talked about, I really never talked about optic nerve. I mean, we have